everything seems to work. Yes. So this is the Google paper, and yesterday we heard from Kujit about the introduction about the surface code, and we learned here about the error rate and how it scales with the physical qubit error rate and the threshold in this t+1/2. And then we also introduced this lambda factor here, that is the ratio of these two epsilon, the error rates, and where d is the code distance, so that it's the ratio of, for example, E3 over E5 or E5 over E7, and that this inversely scales with the physical qubit error rate. Yes, and we looked at some diagrams here about the surface code 357, and then also the logical error rates over multiple cycles here. And it seems like their D7 code definitely outperforms the other ones. And they also estimated here a value of this lambda parameter of like 2.14. So now I'll go a bit more into detail about this logical error, specifically sensitivity. And in order to measure really sensitivity, you need kind of multiple data points of error rates. And kind of a problem of the chip is that you only have one physical error rate, which is determined by values on the chip. And obviously there can be some drift over time, but usually you have one error rate. And what they're doing here is this circuit A, where you have a data qubit and a measurement qubit, and you introduce some intentional errors here. So here they have a continuous Y gate or rotation, and then also a Z alpha rotation, and they inject some error here, and they can change this value of this error by changing the rotation angle alpha. So they kind of start with almost 0 or very, very small alpha values, and then gradually turn them up. And this should, in theory, increase the error rates, as this is not a gate that they consider in their measurement and their evaluation, but rather an error that they kind of assume could also occur naturally. However, this is here confined to like single qubit errors. So here the other things are mostly just Hadamard CNOTs, then some idling of the data qubit, and also some leakage removal, but we'll talk about the leakage in a bit. So the first thing they do here is they essentially start here on the very left here with very small alpha angles, and then they go to the right and increase alpha angles. And naturally, with increasing this alpha angle, you will get higher mean detection probabilities, P-det or P-detection, meaning that if you have a larger alpha value or larger angle by which you rotate, you're more likely to detect this rotation or detect this kind of intentional error. However, even when we don't have any alpha value, we still have some detection probability, because we still have other kinds of errors that happen naturally to our circuit and that are not intentional. So we still have some errors even when alpha is equal to 0. But then we kind of turn this alpha value up here, and eventually what we see here is that we kind of reach a crossover regime or a break-even point where increasing the code distance doesn't actually improve the logical error rate. This is also predicted in predicted in an older paper by them. So this is also from Google Quantum AI, and this is the 2023 paper. And in that one, they also talk about the error rate here versus surface code distance. So, for example, here they have like a scaling factor S. This is like a scaling of the errors, and S is equal to 1 is this 2023 device that they have. and then kind of having intentionally larger errors for like 1.1, 1.2, and so on, or smaller errors for 0.9. And here it seems that for s is equal to 1.0 and 0.9, the logical error rates is decreasing with surface code distance up until like a surface code distance of like 20 on 25. However, if your errors are larger, it's actually better to have a smaller code distance, because for large physical data qubit errors, you can't actually do a very well quantum error correction. So for very large errors, what you kind of end up doing is just having a small code space and having very few qubits and just hoping that you'll get lucky. Because you can't really do error correction if you are above this threshold. And that means that for large error rates, you actually need a smaller code distance. And this is also what we see here, where for large error rates, the smaller code distances actually outperform the larger code distances. However, we are or Google here is with this alpha is equal to 0, which would be the normal operating regime, because in the normal operation they wouldn't insert intentional errors. Here we are definitely in this error where this d is equal to 7 is below the other ones, which is good because that means that, well, error correction works. Yeah, and they also have this inset here where they plot the detection probability against this 1 of lambda factor. And this basically describes that they use this detection probability as a placeholder for the physical error rate. Because in this graph here, they intentionally insert errors into their code or into the circuit. So you can't really talk about like a probabilistic nature of errors. You intentionally always insert some errors. So they kind of replace this with this detection probability here instead.
The error is X, Y, Z, could be either one of them.
I mean, the error that they insert is Y and Z here. But for this detection probability, it just means that any error is detected. Yeah, and basically what they do here, they plot this detection probability against 1 of lambda. And as we previously have seen here, or yesterday by Kurjit, you see that this lambda, or 1 over lambda, scales linearly with the physical qubit error probability, meaning that if the detection probability is a good placeholder for our physical qubit error rate, physical qubit probability or error probability, then this should be also mostly linear against 1 over lambda. And this is in this regime here, between like 0.1 and 0.2, a pretty good approximation. It falls off, however, a bit later here, as we see this starts to kind of bend down a little bit at higher error rates. But yeah, mostly it's a somewhat good approximation. So the next thing here is...
Yeah. So I have a question, like P determinant is for a single qubit, like we were calculating?
Oh, you mean physical or logical?
Yes.
I think this is, well, specifically for the measurement qubits, that the measurement qubits give a wrong result in the stabilizer measurements. Let me check this, however. Use detection probability as problem. Okay, I think it should be in here, but yeah, I think it's that the measurement qubits give a wrong result. So it's essentially related to to physical qubit error rates, but the error could have occurred on both data qubits or measurement qubits. It's just that the readout of the measurement qubits is wrong, as opposed to what you would expect. But you don't really know where this error happened.
So like why they consider the measurement qubit always have a Z error only? Like is it like they consider it already, and the data qubit have a Y error which could be combination, which is like X and Y, X and Z error both, right? So I can think like XZ error. So sitting there in the data qubit, but the measurement qubit have only Z alpha.
Yes, but there is also like a C0 gate, for example, between them, and then also C0 gates to other, like indicated here, to other qubits. So potentially this error could spread among multiple qubits here. But yeah, the only error injected onto the measurement qubit itself is only the Z error. But you will get other errors kind of spreading between data and measurement qubits.
Yeah, so I was thinking like because Z is already there, right? When I'm saying Y, it's like a combination of X and Z error. So it's already coming to the measurement anyway.
Yeah, you
Like
might.
if I did not inject it, like
Oh, you mean that this Z alpha is actually not not another injection, but just the propagation of this Y alpha.
yes, like
Oh, I think
they
they.
wrote it inject error obviously like there, but yeah. So I was like thinking that okay, why it is needed when I already have X and error.
I mean that does make sense. They only talk about okay, like something like okay, this is the injected error. They don't actually specify in the text that this is like a Y alpha on the data or a Z alpha on the measurement. But I guess what you're saying makes sense that they are only injected here in the beginning, actually.
Yeah. Okay.
Right. Let's see. So what they're doing next here is this error estimation, where they estimate the total error by different contributions here. So they plot 1 over lambda as the error rate or error budget. And they have different contributions, for example, from it's a bit larger here, from CZ stray interactions, the data idle, which is this data qubit idling over here, this TD. Then errors from measurement, from leakage, and from single qubit gates. This is also essentially this is already present in some older papers. So this is again the 2023 paper, and here they have a very, very similar graph, again from different contributions. And what they are doing essentially, I haven't looked at this in detail, but they perform different readouts of the logical errors, and then do like a maximum likelihood and kind of plot this against the cause of these errors. And then they kind of somehow reverse engineer when they see different errors and how often they occur. And then they go back to what sources this could have come from. And they essentially end up with this data over here. And
on the y-axis of that, can you zoom in? Zoom into the y-axis, you have this surface called error budget, but why this order of starting from ZZ to leakage is considered here? I don't quite understand the ordering.
I think the order is just in terms of size contribution, I guess.
Only size is important, right? The color size of each box.
Yeah, no, this is just errors adding up. So
we can shuffle the order.
Yes. So I think what they're doing here is just they have a total error budget. They measured like this amount of logical error rate total, and then they try to fit different sources of errors and try to estimate, okay, the errors have to come from somewhere. So basically they simulate a system where they have a contribution of, let's say here, CZ, let's say 0.25 maybe. And this error rate of CZ can't be larger because then you get some different kinds of 2-qubit errors or coherent errors. The point where they are doesn't matter. So I think the plot would be the same if this one Q would be at the bottom here. It's just the amount or the size of the box that contributes. I mean, this dynamical decoupling just sounds like a fancy word for idling errors.
Oh.
For idling errors.
Oh.
So here, what they call this dynamical decoupling means that the data qubit can accumulate some errors while the measurement qubit is performing measurements and readouts. I mean, it could be dephasing, but also decay. It could be any kind of error single qubit error that just happens while your qubit is idling. That could be some drift or other things. Basically anything while this qubit is supposed to do nothing. In theory, if your measurement and readout are relatively fast, this shouldn't be too large of a contribution. So if you could perform faster measurements and readouts, you could probably lessen the impact of this data idle error. Yeah. And maybe let's also talk a bit about leakage, because the leakage is relatively low here as compared to maybe some other cases. And what they are doing to actually decrease this DQLR, which is the data qubit leakage removal. And this is also connected to another paper from them. So here in this paper, this is I think the 72 qubit chip. So this is from October 2023. And they don't actually show. Yeah, I'm not sure, but I think this is the 72 qubit device. And here they compare different methods of how to lessen the impact of leakage on your system. So kind of the approach of doing nothing, they call here no reset. So this would be essentially just do nothing, and essentially leakage will accumulate over time. So they cycle between multiple, or they have multiple cycles here that they go through, multiple iterations of gates and circuits, and they just repeat them, and essentially the leakage and the probability of qubits being in like 2-0 states, for example, increases over time. And this seems to happen for both data qubit and measurement qubits. And the kind of first thing that they're doing in order to improve this leakage is what they call here MLR. And this MLR is the measurement qubit leakage removal. So what they're doing here is, because the measurement qubits don't actually store any data, you can essentially just perform a hard reset on those qubits after each measurement cycle. So they don't need to carry on over any data. So you just take them and do like an unconditional reset, no matter what the measurement qubit is. You've already read it out, and after that you can just do a full reset on it. And this essentially brings down the measurement qubits here in these circles down by a lot. So here you can see there is like a logarithmic axis on the lower side of this graph. And this goes to like 10 to the -4 error rates here, or population. However, this still has the kind of disadvantage that data qubits can still accumulate leakage over time. It seems like the data qubits kind of saturate the leakage population at some point, where they don't grow as much, because you can't really, you can accumulate some leakage in the qubit, but then this population is mostly untouched, where you still operate your code on your code space of 0 and 1, and you just have some population of 2 sitting above there, and does essentially nothing, because the measurement qubits are all in the 0-1 subspace confined. So there's very little there are very little transitions of this 2-0 subspace available. And the kind of thing that they are doing now, this DQLR, which they are also doing for the Willow, essentially means that you perform a swap or an iSwap gate after each cycle within this 2011 code space of data qubit measurement qubit, meaning that you essentially perform a conditional removal of the leakage where you transfer the leakage, the 2-0 state in the data qubit to the measurement qubit. So you essentially start with a 2-0 state and end up with a 1-1 state. And this is still conditional on the leakage. So in theory, you still have this additional excitation in there that isn't supposed to be there. But since it's now in the measurement qubit, you can then perform a hard reset on the measurement qubit and get rid of it, no matter if there was leakage in the beginning or not. So you kind of do you do a little trick where you try to remove the leakage from the qubit without doing an actual hard reset on the data qubit because it stores data. But instead you do it only on the measurement qubits.
And does it require a strong coupling between the readout qubit and the data qubit? Because you will pass on the excitation to the measurement.
I mean, I would assume it requires a decently strong coupling, but then again, the measurement qubit and data qubit need a reasonably strong coupling anyways, because in your cycle, you always have these C0 gates between them in order to do these stabilizer measurements and error corrections. So the speed of your error correction scales with this coupling strength regardless.
Yeah.
No matter if you
of the coupling.
sorry, yes. So this doesn't, or the leakage scaling with the coupling strength is not too bad because the whole error correction scales with it anyways. Yeah, but yeah, this is also what you can see here in the end, where you where they perform this 2 going to the excitation 2 here, going to the measurement qubit and performing then a reset after this. So this is what this remove leakage here is supposed to kind of symbolize. And if they are looking, or if we're looking at the actual data here, we can see that so this is the 72 qubit chip. So this is not the new chip actually, but just the old data, or it's new data, but the old chip. And here the d is equal to 3 surface code actually doesn't improve too much with DQLR. It still sees some improvement, but only relatively minor. However, for the d is equal to 5, this is definitely more apparent. At first I thought, okay, maybe because we have higher error rates for d is equal to 3, the leakage doesn't matter as much. But since this is a linear scale, I would have assumed that this moves by the same amount, even if it ends up being a higher error when compared to the d is equal to 5 case. But I'm not 100% sure, and I don't think they actually say it in the main text, why the d is equal to 3 graph here doesn't improve too much with DQLR. I'm not 100% sure why this is. Yeah, but for the d is equal to 5, this definitely seems to be working much better here, because you can definitely see how we're cutting down on the error probability here pretty reasonably. So without it, I assume the leakage here without DQLR is a big issue, but it seems to be drastically reduced here. Right, and also what they are further talking about here is issues with drift. So here again for the 72 qubit design, they have two setups, the d is equal to 3 and d is equal to 5. And here they essentially perform multiple cycles and then let the setup idle for some time and then perform them again. And they essentially want to measure how big the impact of drift is over time. Here the time scale is hours, meaning that they want to estimate how consistent their chip is over time, or if you were to do very, very long calculations, or even doing multiple calculations that are not connected to each other, but you still want to have consistent results without having to measure all parameters again over time, or doing some fine-tuning each time. So here what ends up happening is you can see that this d is equal to 3 on the individual. You have multiple d is equal to 3 iterations. And here you can see that one of them seems to have a very different logical error rate. So there seems to be one qubit that is pretty bad. And we can also, is it? Yeah, here. So this is the older paper with this 72 qubit chip design. And what they're doing for the d is equal to 3 set is they're trying multiple subsets. So they have like quadrants here. They have a d is equal to 3 quadrant here, then one here, and then one here, and one here. So you have 4 iterations of a d is equal to 3 code within your d is equal to 5 code. And these kind of quadrants here are what they refer to as individuals here. And it seems like one of the quadrants is performing much worse compared to the other 3 here. However, the average of the mean of these 3 distance codes seems to be somewhat unaffected, or reasonably unaffected by this one. And we can also see that over time, the mean of these d is equal to 3 seems to be relatively constant, with some problems occurring here at the end, where it seems like all the error rates go up a little bit here at some specific point. And similar thing also holds true for the d is equal to 5. Here we don't have a mean, we just have one code. And here the error rates are, well, lower than the d is equal to 3. They still seem to vary a bit, because for the d is equal to 5, you don't actually can take a mean value because you only have one code. So this individual levels seem to vary a bit more than the actual average over 4 codes, but it doesn't seem to vary more than the individual d is equal to 3 codes. It also shows similar behavior here at the end where it goes up. This actually suggests to me that they were running the d is equal to 3 and d is equal to 5 measurements at the same time, because they have this same feature here in the end, at the end, instead of measuring them after each other. I'm not 100% sure if this is true, but this is what it seems like.
But then what's the x-axis time? Is it they repeat an experiment over time? Like,
yeah, I think they repeat a measurement each hour. So
and it's getting better and better?
um,
Or at least for that specific first erroneous guy, it falls down
oh, you mean this one
in
here?
the triangle.
I mean, yes, it gets better for this one here. I think overall, in general, you wouldn't expect it to just get better over time, unless you, well, get lucky. I imagine that in this d is equal to 3 code here, there's one somehow faulty qubit, either data or measurement, that is behaving not as you would expect. And it seems like this fixed itself here for some reason that I don't know, and I'm not sure if they don't know. But it seems like this d is equal to 3 code was not great to begin with, but then went down here and was kind of comparable to the others. You can still see some leftover impact on the d is equal to 5 code, so you can see that the error rates also improve here. However, it is much more robust to these individual qubits that are faulty because it is or has a larger code distance. So essentially other qubits need to fail as well or accumulate some errors in order for this one faulty qubit to have a large impact on the whole chip. So you can still see here the error improving slightly at the same time as this improves. But it's much less drastic. But yeah, in an ideal world, you would neither see improvement nor disprovement, worsening, I guess, of this effect. Ideally, what you want is your error rate just being stable all the time and being at the same level. So like a perfectly horizontal line would be the nicest thing here, because that.
They did not plot d equals 7 here, or d equals 7 is lower than 10 minus 3.
Yeah, this is the 72 qubit design, so the old one. They jump around a little bit between the 105, which is the actual Willow, and then the 72, which is the older one. So here, this is less about the new chip in particular and more about scaling different effects. However, maybe they have changed some like measurement details on how they perform measurements on the 72 qubit chip, or maybe some readouts. But in theory, this 72 qubit should behave very similar to how it did in the past. One kind of addition here, this 72 qubit is this code here, but you have additional qubits kind of here around there. So this is why you have 72 qubits, or why they call it 72 qubits, even though you only have 25 data qubits and then 24 measurement qubits, which would mean you should not get 72 qubits in total, but they have some other qubits here. So yeah, they say it here unused. A similar thing also, I mean, Willow doesn't have unused qubits, but it has these leakage removal qubits. This is also why you get 105 qubits instead of 98 qubits, I guess. I think so. Yeah, there are also, I guess there are also qubits here behind the A and the 3, 5, and 7. But yeah, this is why kind of the numbers don't quite line up with this 2d squared minus 1.
When they are like using 72 qubit chip, they still use this leakage qubits, or they don't like.
This.
So they have some leakage qubits also, which was not in the previous chip, right? This green qubits.
You mean in here? In this?
No, now in Willow.
Oh, in Willow.
So there are some leakage qubits they mentioned, right? This green leakage removal qubit.
Yeah.
So I'm seeing this one, like, so like they were not in the previous chip, right?
I mean, the thing is, they say that they are using, wait, I think they're using DQLR here wait, are they? Maybe, okay, let me check. Actually, I'm not sure if they're using, I guess okay, at least they don't mention DQLR. Oh, right, because the DQLR paper is this one here. This is from October 2023. Yeah. And the 72 original chip was from February. So in this one, they don't use DQLR. So they don't need, or they have no need for these leakage removal qubits because you only need them here, these leakage removal qubits, to perform your 2-qubit gates. So I think in this one here, for example, this qubit here would couple to this leakage removal qubit, and then this qubit would couple to this measurement qubit. This qubit would couple to this qubit, and then they would all go kind of downwards to the right and couple to this qubit, and then they hard reset these leakage removal qubits and also measurement qubits.
Yeah, I try to understand like how they operate when they want a 72 qubit operator. Like this one is 105 qubits, something, right? The full one.
I
The
mean,
Willow. And then they were talking about 72 qubit within that.
within that, I mean, do
Like
they?
this one is 105 qubits
Yeah.
when they are going toward D7, and then when they are doing D5 or something, then I was thinking on the same chip or something like, okay, they were doing something 72 qubit.
Smaller subset of qubits.
Yes, but I mean, I think they are. So I think there are two things, because, for example, in this one here, they say they have a d is equal to 5 and in brackets 2023.
Yes.
This refers to d is equal to 5 on the 72 qubit chip.
Yes.
But they
Yes.
also have d is equal to 5 on the 105.
Yes.
And then they refer to performing a subset on the Willow chip.
Yes.
But I think when they refer to later
Yeah.
here, to the 72 qubit,
Mhm.
I assume they mean they performed on the old 72 qubit
Okay.
device.
Mhm.
But they also have, for example, here 105 qubits,
Yeah.
meaning Willow, and then do d is equal to 5 and do d is equal to 3. And I think this one here is a subset, but this one on the right is the old chip.
Mhm.
Right. Okay, let's see. Right. Yeah, right. Leakage removal. Right. We were talking about like how the numbers don't line up. I think we're mostly through this chapter here. Right. What I didn't mention here is that, so with this error estimation that I mentioned earlier, they actually only account for 80%, or they overestimate this lambda with 20%, meaning that the error rate is a bit lower than what it actually, or the estimated error is a bit lower to what it actually is. But they still cover but they overestimate lambda by 20%. So they are off, but they are at least estimating the correct like order of magnitude for these errors with this method here that they like talked about earlier. I think, however, let me check leakage, strain interactions. Right. I mean, yeah, they also mentioned here that these CZ gates are the most or the largest impact here on this error budget. But I think mostly after this they are and so on. Yeah, this is over for the drift here. So for this drift here, yeah, they perform 16 measurements over 15 hours. So each hour they measure once. And I think they talk about pressure 1.1. Okay, yeah. So here in these other measurements, they also recalibrate every 4 experimental runs. Yeah, but they talk a bit about like this drift recalibration. But I think that's about it from this chapter here.
All right. I think we're done, right, with your task.